Hi, my name is Vahan Davoudian. I'm a physical experimentalist for 30 years, and today we are going to demonstrate Earth's rotation by Foucault in 1851. First of all, I would like to thank YouTube for this wonderful opportunity for us. We can upload our videos, some other people can upload their videos, and then we see those, science concepts, we exchange views, and in fact, YouTube is the key to learn, and I think YouTube is like a huge university or huge, network that is connecting everyone. And in fact, I call the YouTube synapse in humans' brains. They are connecting billions of neurons for communication and everything else, and that's exactly what YouTube is doing, and I appreciate they do a good job, and thanks a lot. In fact, this 30 years, whole my inspiration came from animals, insects, sports, and you know what? I did so many experiments, and they're so unique. That's why, 3 months ago, I had unique physics concepts. Because I have never seen this experiment in any physics books. Anyway, first of all, I would like to thank also the YouTube watchers. They emailed me a lot this last few years, and then they just appreciated the work I'm doing because these are unique concepts. And then this is a great encouragement for me, because if there is no feedback, I have no idea how good I'm doing. And I appreciate that. And most of my theories are substantiated by experiment, because I know if there is no experiment, theory is a theory. But my theories are, all substantiated, and I have always replicated these theories as much as I could, especially like big scientists like Newton, Galileo, and all those big like Lenz and the other scientists. So I did my best. If I had all the materials and the tools, I could do those. But overall, I have replicated all of them. And today is so special because this is the third time I'm demonstrating Earth's rotation. This happens in year 2000 in Davoudian University, like 23 years ago in the science club. And then I demonstrated for the science students. They loved it. And now, after 23 years old, 23 years, I realized I must have missed some. And then in year 2010 also I had in CU Boulder, and then also in 2011 in Regis University. And then I realized I might have missed some, but this time is so different. As a matter of fact, I was in France like a month ago. This was the best day of my life because I had no idea. I've been all over Europe, but not in France. And then it took me exactly 3 hours. I scrutinized everything, and then I was there where this happened in 1851. And like I said, this was a great moment in my life because I was not expecting to see such a marvel of engineering. It's called Pendulum. Well, of course, first of all, I have to give you some, history, what that church means, and then how he did it, and then we can go to details. But why this is so important, this presentation, because I scrutinized everything, and then I found so many answers which I watched so many universities. I would say in that maybe like 20-25 years, I have never seen anyone explain why he chose that church, which was 67 meters tall, and it was huge, and then why he chose 28 kilograms Bob, which imagine for 16 seconds is gaining a lot of kinetic energy or joules, and he was genius. And in fact, I had to scrutinize everything step by step. First of all, I'm going to show the posters, and then the second part is going to be the experiment, because I had to come up with my own experiment. I give you one example. If you have two pendulums, and then you release them simultaneously, it doesn't matter, their period, it doesn't matter how long they are, but because my science lab is only 2.8 or 3 meters high, so I had to start with like 50 centimeters and 100 centimeters. If I release both of them simultaneously with great precision, it doesn't matter. because of the Earth's gravity, they just accelerate at the same rate. Exactly the same rate, and the amplitudes are exactly the same. But what I did, it was special. So I released, let me see, I released 15 grams and 150 grams steel balls simultaneously, and then I noticed that they accelerate at the same rate. But what happened after few seconds, that 15 grams is losing kinetic energy, but 150 grams is still oscillating. So that is so important. What Mr. Foucault did was genius. I mean, why he chose 28 kilograms is because of kinetic energy. Was the most important part was that 67 meters is amazing. I believe this was the only place he could find. He could find that 67, and that church was amazing. But let me give you a little bit history about that church. This was This was built in 1758, and then it was completed in 1790 because of financial problems and so many other things. And this is amazing. This is, like I said, marvel of engineering. If you go YouTube, you can see that church is amazing. So it's 110 meters long, 84 meters wide, and it's 83 meters high. What is unique about this marvel of engineering, because I'm a science man, I paid great attention. Instead of one dome, it has 3 domes. So Mr. Foucault had to use the center dome, which was 67 meters or about 220 feet. And the pendulum was a steel wire, and like I said, the bob was 28 kilograms. When we go through this, and then I show you how much kinetic energy this gains, which is beyond my comprehension. And the amazing thing was, his bob had a spike on the bottom, and then I saw everything. It was amazing. And every time this pendulum was swinging back and forth, wow, how genius he was. 16 seconds is a lot in science. I mean, 8 seconds, 1 and then 8 seconds. So each period, because back and forth, lasted 16 seconds. So at the same time, Earth was rotating underneath. And anyway, so, and then it rotated exactly 32.7 hours, and then it went exactly 360 degrees. So he had to invite so many politicians, so many scientists, and then, they just came over because we knew from the Copernicus, from the Galileo, and all those, great Kepler, that Earth is rotating. Well, of course, we have day and night. We can see the sun, and then he can see the solar system. But this was the first proof that, he proved to the world that, Earth is rotating. Well, as a matter of fact, I have never seen such a thing in my life, because he was genius, and I don't know how he could come up with this idea. Well, first of all, he did it in his warehouse, in his basement, and then, like my lab, it was like 3 meters, and then it was not conclusive. But the reason why it wasn't, because it could not go 360 degrees. So is my science lab. In my science lab, it shows that the Earth is rotating. But because my science lab is only 3 meters, my science lab, only my pendulum, I will show by the end of this video, is going only 140 degrees. It doesn't matter, but it shows that the Earth is rotating, because while my pendulum is going back and forth, because my height is only 3 meters, and my pendulum's period is 3.4 only seconds, so what happened, my bob, which is 1.5 kilograms, is going back and forth, and Earth is rotating. Now, I want to demonstrate this. You can see how amazing this marvel of engineering is. I have never seen in my life such a thing. I've been all over Europe, in Italy, so many places, but this was a good experience in my life, because I will never forget how good this was. See, these are the 3 domes. Well, of course, it's not showing here. There's still, Bob is here. You can see on this picture. It shows it's right there. I have another one I'll show you. See, this is a little bit more. Close up. You can see, and what he did was, genius. So this is hexagon, and then this it was in a center. What he did, he put some sand over here. Well, of course, you can see there's a spike over here, and this pendulum was amazing. It was so good. The precision was 100. So every time was going back and forth, or 8 second. So it was going on that sand and making some traces. Well, of course, I show you later. It was like an ovals, or it was like an ellipses. And this is my picture in Pendulum. And then, like I said, this was one of the greatest moments in my life, because some people walked in and walked out like maybe 20 minutes. I had to wait there 3 hours. So while I was making some notes, I got so lucky. There was one gentleman, he approached me, and he was fluent in English. And he was from France, and then we exchanged views, and then I liked him. So I asked so many questions, and he was so helpful. And this one is better. Let me just display this, you can see. See, of course, it doesn't show the sand here, because in 1993 something happened, and then it damaged so bad. So what they had to do, they had to get the original and put it in museum. And this is exact replica, because I had a stopwatch, and maybe I checked this 20 times. The precision was unbelievable. Well, it's a little bit more than 16 seconds, but this was amazing. And now the sand is removed, but this is the original, and this is the original, and you can see unbelievable how good this church is. But there is something important here I have to mention. In order to understand the Earth's rotation, of course we know that Earth is rotating, we have day and night, we have the solar system, but there are so many factors that you have to know. Laws of motion, a Coriolis effect, and then I will show you in a minute, and then relativity, because one of the greatest minds in the history of science was Galileo. And maybe millions of people in Italy watched chandelier was going back and forth. They had no idea, because he was in medical school, and then he saw the chandelier was going back and forth. So at that time there was no clock. 400 years ago, he got his pulse, and they realized all the swings or the amplitudes are exactly the same. So he rushed home, and then the pendulum was discovered. This is the most important thing in mankind history, because the clock was, invented with Christian Huygens, another, genius, Dutch physicist in 1656. And when he did that, the pendulum was so good. This is like a time machine. There was no way, we had to go with the sundial and the other things, but the pendulum was so good by Christian Huygens, and it reduced to 1 second a day. Before was like 1 hour a day, and then it was falling behind. Even though that was mechanical, it was okay all the way to 1930s. And after that, the quartz was there, and the precision became 100%. Nowadays we have atomic clock, and the precision is 1 second in 5 million or 5 billion years. So anyway, and then Galileo's, relativity is so amazing. It is not Hendrik Lorentz or the other. It's not complicated. It's so easy. You have to have frame of reference. If you don't have a frame of reference, you won't be able to tell what you're doing. For instance, the best example is I'm walking 5 miles per hour. So my frame of reference is Earth. So I'm walking on the surface of the Earth. So Galileo did the same thing. He said, in order to perceive, or our perception depends on where you are, and we have to have a frame of reference. And then he was under the deck in a ship, and there was no way he could tell he was traveling, because you could turn on the engine and then make noise, and then he was thinking, well, when you open the window in second floor, deck, and then he realized, he was comparing the shore to his ship, and the ship was moving. So we do exactly the same thing. Our pendulum, the reference is this. So we have this. So we are comparing our pendulum is going back and forth. At the same time, this, me, those guests, and everyone else, we are rotating with the Earth. But the pendulum is not going with the Earth. That is so important. I had to screw the nest for so many years, and finally I found the problem. And I'm glad, I have a generous offer for you. Any universities, or any college, or any even, high schools, if they want me, I can come over with my expenses and demonstrate this with great precision, and I will pay for all expenses. And let me show you my email and everything else. So the reason why I do this, because I want to promote science. So this is my email. So this is my email. Yeah, right there. Vahan, Davoudian, 1948 @gmail.com. So, and then another important thing is the kinetic energy. I will explain that later. But the most important factor, he was so successful, I scrutinized real good, and then I found the question. First of all was gained kinetic energy, because 28 kilograms is so much. Especially my pendulum is going like 3.4 seconds. His pendulum was going 16 seconds. And imagine, in science, 16 seconds is a lot. It's astronomical. At the same time, Earth is rotating underneath. And this is the one I came up with. Not only you have to do this fact, but also you have to understand the latitude and longitude. What I did, I learned this in electronics, because I call this a roll and unroll. I was investigating for researching for magnetic levitation. It was year 2000, and then I realized magnetic levitation is exactly like an electric motor, which has been opened. But if we close that, it's going to be like an electric motor. And then I remember in 1992, I was in Magic Mountain. It was the same thing. It just happened that operator was so good in physics, was explaining, and then I was explaining my views, and then we became friends. And imagine, in 6 seconds, Magic Mountain, you can accelerate to 100 kilometers. It's beyond my imagination, beyond belief that how good is what? Attraction, repulsion, attraction, repulsion. So I believe this roll and unroll is playing extremely good idea in my life. And imagine, this is the one, it's a word map. I call this unroll. What it is, if I roll this, it becomes a globe. But you can see here longitude and latitude. If you don't have this frame of reference, you have no idea where you are. Of course, nowadays we have like Greenwich in England, and then it's going north-south, and then we have latitudes, and each one is imaginary lines like 15 degrees. And imagine the satellite can pinpoint almost like 10 centimeters across. Like 30, 40 years ago, we didn't have this technology. So and then I will explain this later. But this was my imagination that, you know what, if you want to see what the Coriolis effect is, you have to compare it with the merry-go-round. And this was the best example I could do. And then you can see how easy it is to understand what I mean by merry-go-round, or, you know, by, carousel. See, there is an important factor here we call it Coriolis effect. Because he was great French scientist, and he says if we have accelerating frame of reference, and then not on the surface, on top, let's say if I'm firing a shell like 40, 60, 70 kilometers, that shell is going to deflect. Why? Because of Earth's rotation. That is amazing. I mean, this discovery was so amazing in the human's life that it changed our understanding for the Earth's rotation and so on and so. Of course, I give you an example. In World War, England never fought in the Falkland Island, which was southern hemisphere in South Argentina. But you know, they were firing shells, and then they realized instead of landing exactly what they calculated, it was 6-7 meters away. They had no idea, because always England fought in northern hemisphere, not in south. The reason why Coriolis effect tells us everything is deflected to the right, and then in northern left on northern hemisphere, and southern hemisphere is going to be right. And then we can see, you know, cyclotrons and everything else is like that. And I came up with this idea that, you know, how easy it is for the student to understand this, merry-go-round. If a baby is sitting here and another one sitting on this edge, and merry-go-round, I would say maybe it's like 10, 12 or 15 meters, and then as long as this merry-go-round is stationary, it's okay. I mean, Bob can throw a ball for Julie, Julie can do the same thing, and they catch easy. But what if we, you know, turn this on? It doesn't matter, clockwise or counterclockwise. So Bob is throwing a ball, and the Julie cannot catch the ball. The reason why? This is accelerating frame of reference. So accelerating frame of reference. So Bob or Julie will miss the ball because it's going in rotation. Latitudes are so important. I will show you. See, like if you go like 30 degrees, Earth is different. If you go on 45 degrees, Earth's rotation is different. If you go to 60 degrees, it's different. 75 degrees is different. Well, of course, I have a good experiment I show you. You'll be amazed how I prove that for the student it's easy to understand. And one of the breakthroughs in my presentation today is this. Let me show you. And I'm so happy I came up with this idea. It took me almost a month to calculate this. It was not easy. We are located in Frisco, Texas, and then this happened in Paris, and imagine it's 48, well I put 50, it doesn't matter, it's the same. So Earth rotation at that point is exactly 1,073 kilometers. I had to convert it to meters per second in Paris. While the pendulum was going back and forth in 60 seconds, and the Earth was rotating 298 meters per second. So imagine what happened. This was amazing. It is exactly like Lorentz transformation. So they are different velocities. So pendulum and Earth are not the same velocity. So pendulum was going back and forth, and this lagging acceleration is lagging behind. But it doesn't matter. Earth is rotating exactly with the same speed at 298 meters per second. But let me tell you what happened in Dallas, Texas. Let me see here. Let's see here. Yeah, this is Dallas or Frisco, the same anyway. So in Frisco, Texas, which is almost like 30 30 degrees north, Earth rotates 1,446 kilometers, and this is exactly 401 meter per second. So what happened? My pendulum is not like focus, because it's only going only 3.4 seconds, but it doesn't matter. It shows the principle. But imagine this 298 meter. That is a lot. So what happened that 16 seconds is going back and forth, and imagine Earth is rotating kilometers. But why? Because at that latitude is different. So this is another one. I have to show you. Well, of course, you have to wait. When I start my, pendulum and the others, you can see exactly what I mean, because I have so many experiments I show you, because I had to start these. Unfortunately, I have no help today to film everything, so I have to do it by myself. And pendulum is easy to understand. And the formula is like this. T, which is the period, every time the pendulum goes back and forth, they call it 1 period. And this 2 pi, and then it's, square of length divided by acceleration. So 67 meter, then it's going to be exactly 8.185. This is the square root. And in fact, I came up with the easier answer for myself, so I don't even have to use the formula. If I get the square root of 67 meters for the focus pendulum and multiply it by 2, I come up with exactly the same thing. So, like I said, I was in that, Pendulum for 3 hours, and then that was amazing. That was a great moment in my life, and then I realized that that pendulum was so good, and then God knows how many times I did it with my stopwatch. It was, well, of course, it's a little bit more than 16 point, but I'm going to 16 seconds, and that's what happened. It was going back and forth. But the important fact is, we have to realize 16 seconds is a lot. So he was genius, he come up with such a height, and then the second important factor was the kinetic energy. I show you the kinetic energy now. Well, of course, there are so many proofs for the Earth's rotation. Let me give you the old examples. I remember when I was in high school, maybe like 11 years old or something like that. This was our idea, and it was so easy. Let me show you. Well, of course, at that time, Mr. Foucault did this pendulum, but I don't know why we're behind the science. One example is like this. If you go on an Empire State Building, it is 385 meters, the height. If you drop a ball, let's say 1 kilogram steel ball, well, of course, there is no doubt we have friction and everything else, but something amazing happened. The ball is going to accelerate 9.82 seconds, and will take exactly 38.8 seconds to hit the ground. But that's not the point. The point is, at the time, ball is coming down in free fall, and there's nothing, except the gravity and the Earth's friction. At the same time, Earth is rotating. If we have a laser beam, and it shows that, showing the Empire State Building exactly perpendicular where, the ball should come down, it doesn't, because it's going to be deflected. The reason why, at the same time that 38 seconds the ball is falling to the ground, Earth is rotating. The oldest, they would do it, well, of course, at that time there was no, buildings or anything like that. They would do it from the churches and things like that. And like I said, I came up with my own idea. If you have a helicopter, and the helicopter is hovering like 400, 500 meters, above the surface of the Earth, and we make sure that helicopter has a laser beam, and then it's just projected to the ground, and then we drop balls, that is not going to be the same. If you increase the height, it's going to be more. If you decrease the height, we come to 100, that deflection is going to be less. So that is the proof that the Earth is rotating. But, when I compare this Earth's rotation, I will show you in a second, I realized that Austrian physicists did something amazing. And some people mistake this with the toilet bowls and with some other things. Well, of course, that is not true because toilet bowl is so little. So he did amazing experiment. This was Austrian physicist, and then he did this huge tank. You see, it's 5 meters, and then it's all 2 meters deep. What he did was genius. So he just filled this with water, and he waited 2 days. Make sure everything, there's no earthquake or anything. And then he was so genius, he put a plug over here. So 5 meters divided by 5 centimeters is 100 times larger. Imagine, see the ratio is 100 to 1. So 5 meters or 500 centimeters versus 5 centimeters. So what he did, he made sure it was was stagnant. Then he put some styrofoams on the surface of this water, and he waited. And then slowly he removed the plug. After a few minutes, he realized those styrofoams are going clockwise. That's exactly what happened with the focus pendulum. It's going clockwise, 11.3 degrees per hour. And then he realized this styrofoam is going, and this is an amazing idea. This is called conservation of angular momentum. So what happened? They're going clockwise. Well, of course, we know that you had to use wood or, polystyrene or peanut or something like that, so they would float on the water, so they wouldn't sink. That's exactly what he did. And then they were going back and forth. They were going like this, so it's called conservation of angular momentum. Well, at the same time, I don't want to complicate things, it's also Earth's differential forces and Coriolis. Because I remember year 2000, I had a theories for the free-falling object. If you watch that, you'll be amazed how great I explained everything for these differential forces. And then you'll be amazed that, I showed that if you hang something suspended in air, it's going to go counterclockwise. It doesn't matter for the weight, but if you have more weight, it's going to be inversely proportional to the, weight or the mass. If you have less, it's same. But if you go to southern hemisphere, instead of counterclockwise, it's going clockwise. So it's the combination of, differential forces, Coriolis forces, and Earth rotation. Something amazing happened also for the Earth's rotation. I don't know why. This was another great moment in my life because I'm so adventurous, and then it just happened. I invited everyone to Florida. This was in 1995. Let me post this picture, you can see it. This was in 1995. That was 12th of November 1995, and this was a space shuttle Atlantis, and we were so excited. And then this was almost like 30 years ago. So I invited everyone. We had some company, and my kids were so young. They said, "You know what, Dad? We're not going to get up so early." I said, "No, we have to. This is one time, one of a lifetime event." So we got there early in the morning, and then they had to, launch this. This was a great moment in my life. So anyway, I don't know what happened. I got lucky again. While we were talking to someone, I saw someone. He was a physicist. I said, "Wow, my God, this is a good moment in my life." And he was from NASA. As I was, talking about my experiment and so and so and so, and then he was so happy, We exchanged views and so on. So he says, do you know that the reason why we launched this Atlantis or any shuttle toward the east? I said, I had no idea. I didn't know that. He said, sir, why do we do this? He said, because of Earth's rotation. Even though it is not touching the ground, it is not touching the Earth, it's going toward the east, because see, it is in air. But you know what? That is boosting a little bit. So this was another good moment in my life, and I'm glad we saw this in 1995, and it was called Atlantis, and it was STS-74. So I analyzed this, see how genius he was. I mean, Mr. Foucault. Now I have to explain about gain kinetic energy. See, my bulb, my science lab, I used 12 centimeters, across crystal ball, which is 1.5 kilograms. So 1.5 kilograms versus 28 kilograms is a lot. So what Mr. Foucault did was amazing. So he had this 28 kilograms. By the time it was going 8 seconds back and this way, 8 seconds the other way, 16 seconds, gaining a lot of kinetic energy. So let me show you here. So if you go, you have to know this formula, which is one of the most important formulas in the science. I would even compare this EMC squared. This is more important than EMC squared. Anytime you have anything in motion, you get kinetic energies. Ke half mass times velocity squared. But something amazing is here. If you increase the mass by 2, so kinetic energy is going to be 2. If you increase by 2, it's going to be square. So imagine how much joules Mr. Foucault did for that 28 kilograms was amazing. And I was thinking, why Mr. Foucault used only 6 meters across? Because when I show you this picture for the Pendulum, the whole thing, the bob was going 6 meters. I would say 3 meters on inside, roughly. And then that hexagon table, which was sand on it, that was, I measured almost like 1.6 or 1.5 meter by 1.5 meter, but it was showing those ellipses, and as the kinetic energy was getting less and less, those ellipses were getting sharper and sharper. And this is my, I show you in a minute. I had like 50 centimeters, and then the period was exactly 1.4 seconds. I had 1 meter, and then the period was exactly 2 seconds. And then I had 2.8 meters, and then it was 3.34 seconds. And Mr. Foucault had 67 meters period, which was 16.423 seconds. So imagine that was the important part of his experiment because of these 2 factors. But now I have to mention something else, which was, it changed our life. And I don't know why scientists never mentioned this. Mr. Foucault did the pendulum. Of course, there is no doubt this was the great invention after Galileo and Émile de Châtelet, and then everyone else, Sir Isaac Newton, but perfected by Christian Huygens and so on. So, but something amazing happened in our life. He had the gyroscope. And that is more important than Foucault's pendulum, because anytime I go to any science lab or university, I can see they make a big deal. Well, of course the Foucault's pendulum is so good, they have to analyze what happened. But in 1852 he came up with gyroscope. That is more important, because after like 82 years we are still using. Without the gyroscope, we're lost in space. Without the gyroscope, we're lost in, if we're in a submarine, the ocean, we're lost. If we're mining a tunnel, we're lost. If we are, in a space station, we don't have frame of reference. The reason why I'm on Earth, I'm driving my car, I have a frame of reference. Earth is my frame of reference. But while I'm in space, I don't have any. Everywhere is blue. I have no idea where Earth is, where South is, where North is. But imagine after so many years, now we have incorporated the gyroscope with compass. All days they would say, this is north, this is south. Well, of course, that's okay at that time. But now the precision is 100%, not maybe 100%, 99.9%, because we are using gyroscope with gyro compass. So we have both compass and gyroscope. So what he did was amazing. And this gyroscope changed our life, and how important it is in our life. And imagine, without the gyroscope, there is no way we can go to space. I remember I watched the, International Space Station. Sometimes they use 8 or 9 or 10 gyroscope. Isn't that amazing? So what it is, I have to explain a little bit. It doesn't matter. The torque is not, any torque is not causing, or any force is not causing torque on it, because the reason why this man was genius, the way he built this, there is no way you can cause torque. But of course, there is a point here, that gyroscope has a disc. That disc must rotate so fast, and there's an angular momentum, conservation of angular momentum. So that's what happened. So what I mean, it is so important in our life. Now I'm going to demonstrate this. Of course, I was going to buy gyroscope and then I didn't get chance anyway. So, but that's okay. You guys have seen it in science videos and so many other things. But this is a genius idea. Why it's a genius idea? Because I think his idea was people were not satisfied with the pendulum. Of course, they were 100%, but they were so jealous, especially the politicians, especially the scientists in France. They did not formulate that, and that was so awful. That is one of the bad moments in the history of France, or why they did not cooperate with him. Well, of course, he could have, but they could come up with a formula. So what it is, imagine. These are called gimbals, and this is free rotating, see? It can go any orientation. This is also free rotating. But see, this one, the frame is stationary. So if I tilt this, see? They go this way, that way, up and down, up and down. But there's something important here. If this disc is rotating, see, this is in the center. There is no way, it doesn't matter how I tilt this, it's going to be the same. So nothing will affect that. Why? It's a conservation of angular momentum. Well, of course, nowadays they have electric motors and so and so. So as long as this disc is rotating, it doesn't matter, clockwise or counterclockwise, and then you cannot cause any torque on this. So let's say space station is here, now it's going this way, it's going that way, it's going that way, but it's showing our orientation, because we have to go around the Earth 60 minutes. So it's going around the Earth, 90 minutes. So we're going around the Earth 90 minutes. So this is so important in our life. And then I had to go back to my childhood, like 6-7 years old. And I don't know why I realized this was a great idea in my life, and I was playing with this all day long. And then I said, Vahan, if you remove this disc from the gyroscope, it's going to be top. That's what you were playing. You were 6-7 years old. But let me show you one. Okay. This is the top. Let me show you. See, it doesn't matter how I rotate this. See, it's not going to fall. See? You see what happened? It's not going to fall. Because the reason why, as long as this is rotating, you imagine, this is like a gyroscope. I mean, see how easy it is for the student or the science people to understand. You don't have to have a big gyroscope like this. You can demonstrate this with this simple idea. Look, see? See? Tilting. But see what happened? It's not falling. The reason why? It's not falling, see? So, I realize if I demonstrate this, people will be able, I mean especially science lovers or the physics lovers, will be able to understand exactly what I mean by that. So, this is the second part I told you about kinetic energy, because I mean, like I said, without the gain kinetic energy and without that long 67 meters, pendulum, he could not demonstrate the Earth's rotation. Well, of course, I have to mention something. It is not the same in everywhere. In Texas, it's different. In, like New York City is different. In each, latitude is different. Well, of course, I have a good experiment I'll show you guys in a minute. Let me see if I can do that. Okay. I remember this was in DeVry University, and science classes, they were having problem with, what do we mean by work? So every time the pendulum going back and forth, because see, thermodynamically we are not in a closed system. Air is there and is doing some work. And I remember one of the students was so smart, he approached me and said, Vahan, what do you mean what is doing work? I said, I can prove it for you. You don't see, but every time this bob, it doesn't matter how small or how big this bob is going back and forth, and it doesn't matter the periods, 2 seconds, 5 seconds, 10 seconds, is doing some work. And then he did not understand. DeVry was close to my house. And then I had to come up with this idea. And then next time I took this to a professor, he loved that. He patted me on the shoulder and said, Vahan, thank you for this. What very expensive, scale. And you may not believe it's 2 micrograms electronic. And the 2 microgram is 0.002 milligram, and 1 milligram is 1 microgram, which is equal to 0.001 milligram. So anyway, I had this bob, let me show you. Well, of course it wasn't like this, it was a huge bob. So I was swinging back and forth on my scale. Let me see where my scale is. I think it must be here somewhere. Yeah, it's here. Let me get my scale. So this is my scale. Well, of course, unfortunately, it doesn't show, because if I turn this on, I don't have my help today, and then I'm by myself. This is showing microgram. So the faster it goes, the more air is displaced. So what happened in a factory is, scales like this always, they calibrate with 14.7 atmospheric pressure, and the precision is almost 100%. And they saw, because the one I had was much bigger than this, and then somebody zoomed on this. So every time this pendulum is going back and forth, the bob is going back and forth, is almost displacing air, which was my, bob was almost like 25 centimeters, 6 times bigger than this, so it was displacing air. So they didn't understand exactly what I mean, and then after that they knew that, so every time, something like that happened, it's displacing. And then I came up with this idea for my pendulum, because this pendulum is going, north-south, at the same time is rotating with the Earth's rotation. So I had to come up with this idea, which was a good idea. So I have one ball bearing horizontal and another one vertical. So what it is, this is independent from this ball bearing, so this can go north and south, this can go 360 degrees. So they love this idea anyway. So now I show you more experiment, but like I said, I have to emphasize this kinetic energy again, and kinetic energy was so important, and it took, God knows, maybe 32.7 hours for the Earth to go around. Another important fact for the pendulum is called restoring force. Imagine if I have a pendulum on Moon, it's not going to be exactly like Earth because it's 6 times less acceleration due to the gravity. And besides, there is no atmosphere in Moon. It doesn't matter. But if I take my pendulum to the Jupiter, it's going to go more. The reason why is 2.4 compared to Earth, and Earth is 9.8. 1, and then Jupiter is 2.4 compared to Earth. So that is so important. So the faster the pendulum goes, the bob goes, it displaces more air. When I watched in France, I realized this guy is genius. It was so slow, and then I recalculated, I realized Mr. Foucault did the right thing. That 160 centimeters, half of it was, let's say 2 meters, was going extremely slow. What if I came up with this idea? Mr. Foucault was using 70 meters, which is the width of the Pantheon. That would make a big difference. He could get a lot of friction. He could get a lot of, so that's why he used that 6 meters, and that was another point in his thing that, he didn't do it. So I'm glad he did this, but mine is maximum, I would say, my car garage, my science lab is not that big deal anyway. So, but this in physics, we call this trade-off. So if you have big bob, his bob was almost like 25 centimeters across, but that was not important, because important thing was the kinetic energy was so huge, the height was unbelievable, and then the earth resistance, honest to God, I would say it was 0. So this is called trade-off. So what happened, if the faster pendulum goes, the acceleration goes down. If you accelerate less, and there is no air resistance. So that's what happened. Okay, this is another one. So I'll show you in a minute. Like I said, simultaneously I released 2 pendulums, and what happened after a few seconds they go out of synchronization. The reason why I wanted to prove to the world that the kinetic energy Mr. Foucault did was amazing, and then he made a big difference. So I show you here one. Okay, now I'm going to have to use my, unfortunately I have no help, I'm going to have to use my light and then use this a little bit further so I can show you more experiment for my science lab. So just excuse me for a second. So these are the one I did. Let me adjust this a little bit. I'm sorry for the inconvenience because, like I said, my help is not here today, and I have no choice to do it by myself. And I know I don't want to interrupt everything, but sorry about that. Yeah, so let's see. I can do it like that. Okay, fantastic. So let me come closer so you can see what I mean by this pendulum, and you can see exactly what I mean by this. If you watch closely, see what happened here. That is so amazing. See, I got two pendulums here. This one is 15 grams and this one is 150 grams. See, I release them simultaneously. And it's the laws of physics. The amplitudes are going to be exactly the same. See what happened? They're going the same. But after a few seconds, see what happened? The smaller ones goes out of synchronization. The reason why that one has 150 grams mass, this one has only 15 grams. So it's 10 times more. You see that is going this my graduation, this is going to 8, and this big one is going to 11. See my graduation there? But that's not the thing. And if you watch closely, you can see this will stop after 4 minutes. 150 grams stops from 12 minutes. So that's exactly what Mr. Foucault did. And I proved that, that's what he did was based on science, and he was a great physicist, and then he did a good job. Well, of course, I don't want to waste time. Now I'm going to stop this, and then you can see how important that was. Now I'm going to show you another thing that, if you watch my videos in year 2000, it's called the theory of free-falling object. I explained to the best of my ability, and I remember I did this. Imagine we have two balls like this. So what it is, my great inspiration came from Galileo, but I had to invent my own. Galileo used only one ramp, but I had to bend my ramp. See, this is a plastic. And it's a perfect ramp because the friction is so good. But see what happened? That the smaller mass is going to stop in a second. Look, see? But the big one, which is 10 times more, is going to go forever. So this is another case for the kinetic energy. And I'm glad I did this. Well, I just don't want to waste more time. They go forever. So let me stop there. And in fact, there's another thing, I have to show you this. This is, you see how big difference it is. You can see exactly what I mean by what Mr. Foucault is. This is exactly 11.4 kilograms. If I exert force on this, which I measure, it's like, I would say, 50 Newton force. It rotates 17 minutes. Let me make sure it's adjusted. Let me make sure it's adjusted. Yeah, it is. And then I had a wooden one, which only rotated only 40 seconds. So imagine how important it is. See, it goes forever, so I'm going to have to stop it now. So I'm not going to go forever. But see, I didn't increase the force or anything. It's exactly the same. It's so hard you can't even sometimes stop. This experiment was fantastic because people loved it. Let me go back here. Of course, I'm going to have to remove these so you can see exactly what I mean by this experiment. It was difficult a little bit, I was demonstrating in year 2000 in CU Boulder for the student that what do we mean by the different latitudes, they have different, acceleration, different speeds, and then I had to show on this globe, but it didn't help that much. So I came up with this genius idea, let me show you. So I had to use, if you remember a few minutes ago, I said you can compact the Earth, make it like this. So I had to use this. So what it is, I have North Pole, I have like 40 degrees latitude, and I have equator. So this one last is the equator. So I realized if I have like ball bearings, and then every time I rotate, see what happened. The one in the North Pole hardly rotates. The one in a 40 latitude rotates. But the one in the equator rotates a lot. So let me see if I have the thing here. Imagine North Pole in 1 hour goes 8 seconds. 8 centimeters in 1 hour. And then I came up with another idea like this. Let me show you this one. Let me see where that thing. I had the same thing, and then if you have a globe like this, if you rotate this one in the North Pole is going to be hardly, but this one is going to rotate more, and this one is coinciding with, with the equator, it's going to go more. Let me see, where did I put that? Oh, right there. Okay, see? I have it. So this is the North Pole, this is the 40 degrees, and this is the equator. If I rotate the Earth, and then they did understand this perfectly. See how easy it is? This is a genius idea, so you can visualize, you can conceptualize exactly how the Earth is rotating. And if you go to the southern hemisphere, it's going to be the opposite. Okay, now the last part is my pendulum. I have to turn my light, but before I do that, I have to show you one thing I did, which was a good idea, and I think you might love it. So this is a laser beam. This is a laser beam, see? So what it is, I made my own pendulum. Why did I do this? Because I didn't want to use sand or anything like that. So let me show you what I mean by this laser beam. Okay, so see, the reason why I did this, like focus pendulum, this is going to show exactly how when the Earth is rotating, this pendulum is marking big ellipses, or those ovals. Let me show you. Let me set this aside so it won't be in a hurry. So if you watch this, you can see, let me go a little bit further so you can see the entire thing. This is exactly 1 meter, and let me see, yeah, here is good. You can see here much better. So this is the laser beam. So if I activate this now, you can see how good it shows Earth is rotating. Did you see? After a few seconds, it's going like 20 degrees. See? Now, after 8 oscillation, it's almost 90 degrees. Did you see what happened? Well, of course, this is going to go forever. Don't want to do that. So I just stop this. And this is my main. I have to change the lights a little bit this way so you can see my pendulum here. This is my pendulum, but I have to adjust the light so you can see. Okay, so you can see I put longitude, latitude, and in fact my car garage or science lab is showing this is north. So let me make sure this shows everything. Make sure it's adjusted so you guys can see my pendulum. Okay, this is my pendulum, and I think it shows now everything. So if I activate it, you can see how good it shows while the Earth is rotating, the plane of oscillation is changing. Let me show you. So it's going clockwise, you can see. You can see it's going clockwise and the plane is changing because see, you can see equator, you can see longitude, but you can see Earth is rotating underneath. Well, of course, like I said, my pendulum, because the height is not good enough, but it shows the principle. It goes maximum 140 degrees, but you can see how easy it shows the pendulum. Let me show one more time so you can see. Let me show you one more time. And it's always going clockwise, and like I said, depending upon the latitude, it can go forever. But like I said, unfortunately, I couldn't find any, because my science lab is only 3 meters, but I remember I used to work in an English company, and the warehouse was so good, and I did that in year 2000. That was like almost 15 meters, but unfortunately, we didn't film that part. You see what happened? It's going clockwise, but now after 6 or 7 oscillations or periods, it's going like 10 degrees. Now it's going like 20 degrees, but you can see your frame of reference is the Greenwich. You can see it? But it's going to go all the way by the time it's 28 or 26, I would say, oscillations or periods, it's going to go 90 degrees. See, now it's 40 degrees. See? Did you see what happened? Well, of course, I'm going to have to display these so you can see. See those, round things? So every time focus pendulum was going back and forth, was tracing on that sand. Because I couldn't do that anyway, but I had to do it with a laser beam, but it shows that exactly what happened. Now I have 2 more experiments, and I'm hoping, I have covered everything. And, I apologize if my helper was not here, and I had to interrupt some. Let me get another 2 more experiments, and then you can see. I have to stop this because this is going to go forever. Okay, this is another thing. In order to prove that while Earth is rotating, we can have, let me come closer a little bit, you can see. This is very important experiment, and I have never seen anyone did this anyway. I have never seen this because it's very important, this experiment. It's extremely important. Let me show you. So what it is, you can see, I have pendulum, but the important part is that pendulum is in the center. Let me show you. Yeah, see? The pendulum is in the center. Let me come closer a little bit, you can see. Okay, you see what happened? If I swing this back and forth, I can rotate the Earth underneath. But before that, I have to show you something. It was a genius idea. I came up with this. See, this dial is so amazing. In my cell phone, you can get the orientation, north, south, or whatever. And then, I came up with this good idea that, I can use the same dial, but mine is manual. In your cell phone, if you turn left, right, up, and down, your orientation is changing. North becomes south and south. But mine is different. Let me see if I can show you a little bit better. You can see it much better. See, like this. If I turn this knob, turn this dial, you can see north becomes south, south becomes north. The only difference my dial is, mine is manual, and the phone is doing with GPS. Mine is not connected to GPS, but it shows the principle, see? It shows southeast, northeast, southeast, northeast. So, and this was so important, and I don't remember having done this before, and I came up with this after I came back from France, that this is very important, and I'm glad you'll be, amazed when I did this experiment. See, when I swing this is exactly 500 grams. See what happened? I can rotate the Earth. But see what happened? Oscillation won't stop. Did you see what happened? It doesn't matter. You go north, You go clockwise or counterclockwise. So, see? It doesn't matter. It won't stop. Because Earth is rotating, but because of inertia, this is going back and forth and back and forth, back and forth. So I just wanted to thank, it was a long video, and I appreciate you watched it. And then, like I said, your admiration, your encouragement is so important, and I'm hoping you guys can subscribe it, and then email me if you have any concern. Maybe I didn't cover everything because I didn't have my help, but anyway, I have more experiment I can show, but I'm glad, I covered almost everything. And like I said, two important factors were the length and the gain kinetic energy, and you can see that the Earth is rotating, but the pendulum is nothing to do with it. It's just going because of gain kinetic energy and the inertia and this lagging behind. Thank you very much for watching, and I'm hoping you enjoyed the video. So every month I have I have uploaded 43 theories. I have more theories, and I'm hoping I can do that every month. And then I'm not that busy, so I'm hoping next month I can do more. And these are for the Michael Faraday and the others. So I'm hoping you guys can enjoy it. Thank you very much for watching, and that was great honor. Your encouragement helped me a lot, and I'm always enthusiastic to come up with more ideas. And then my main objective is to encourage the young generation to activate your sense of wonder. That is the important factor for me. Thank you very much for watching, and I'm hoping you enjoyed the video, and thanks a lot.